Wait, you think making all numbers equal is easy? What if I told you? Sometimes it's impossible. And when it is possible, there's only one correct target value. Choose wrong, and you waste operations. Want full solution? Check this video.
Hi everyone and welcome back. Today we are solving a really interesting problem from lead code called minimum operations to make a uni-value grid. We are given a 2D integer grid of size m multiplied by n and an integer x. And in one operation, we can add x or subtract x from any element in the grid. We need to return the minimum number of operations to make the grid uni-value. And a uni-value grid is a grid where all elements of it are equal. And if it's not possible, we need to return -1. So now here is the first key observation. If it is impossible to make the grid uni-value, we need to return -1 immediately. But when is it impossible? It is impossible when if the difference between numbers is not divisible by x. Which means, let's look at this example. Here, we need to make all the elements in this grid equal. So we choose to make every element here equal to number 4. So we need to make sure that every element other than 4 can be, by adding x or subtracting x, reach the value 4. To make sure this operation is valid, we need to make sure that the difference between any number in the grid and the number 4 is divisible by x. In other words, all number must have the same remainder when divided by x. So, step 1 to solve this operation or this question is to first we need to flat the grid into 1D array. And then check that all elements have the same remainder if it's divided by x. And if not, we return -1. Let's look at this in the code. First, we need to flat our grid. So we will define a vector of end. Let's call it nums. And also, we will define a variable, call it reminder, and I lose the first element in the grid. And I'll get the reminder if it's divided by x. After that, I will iterate over each element in the grid to flatten the grid. I'll check if each value in the grid, if we divide it by x, it will return the same remainder of our stored value here in the remainder, and if it's not, we will return -1 immediately, and this means that it is impossible to have a uni-value grid. Otherwise, I'll add the value to our nums vector. So this loop will flatten the grid. Now it comes the most important insight, which is we need to minimize the number of operations to make the grid uni-value. And to do so, we should convert all numbers in the grid to the median. Why the median? Because the median minimizes the sum of absolute differences. This is a classic trick in optimization problems. But to reach the median, we need to sort our flattened array, and this will take O of n log n time. To make it better, instead of sorting all the elements in the array, we can do better by using the nth element API, which gives us the median in average O of n time. So here in the code, first I'll get the size of num, and then I'll call the API is element. I'll give it the nums dot begin iterator and the nums dot begin plus n divided by 2 and the nums dot n. Here I'm sorting the nums array up to the median element. So the median after the sorting will be located at nums of n divided by 2, the middle element. After that, we need to compute how many operations do we need to reach a uni-value grid. And to do so, I'll define a variable called answer that will hold the final answer or the number of operations at the end, and we will loop over the nums vector, and our answer we will append or add to our answer the absolute value of nums minus median and this is divided by x, and at the end we need to return our answer. So here we are looping over all the elements in our flattened vector, and we check the difference between that element and the median value, and we divide it by x to return the number of operation, and then we add the calculation of this equation into answer, and at the end we return our answer. And that's it. So to summarize, first we flattened our grid, then we check the visibility using the modulo of x. After that, we find the median element, and finally we compute the total operations. So let's run it to make sure it doesn't have any errors and submit it. And as you can see, this problem looks tricky at first, but once you see the median trick, it becomes much easier. If you found this helpful, don't forget to like and subscribe, and I'll see you in next problem. Happy coding. Bye.